So we just discussed what is a mean vector, what is a population mean, sample mean, and how to compute variance and covariance. So now we will be discussing what is correlation and how to compute correlation, and we will be discussing three different methods of computing correlation with examples. Okay. So here you can just see three different types of graphs. In the first graph, you can see when the x values are increasing, the y values are also increasing. So we can say there is a positive relation between the x and y axis values. Here, when the x values are increasing, the y values are decreasing in the second graph. So we can say there is a negative relation. So when one value increases, the other value is decreasing. Okay, and it's vice versa. And in the third graph, you can see there is no relation at all. Okay, so we have been discussing the same in graphs in the covariance concepts as well, right? So here, with covariance matrix, we can able to find out is there any relationship within the two random variables x and y, whether it is a positive or negative. But we cannot compute what is the degree of the relationship between these two random variables. Okay, so for that we use correlation. So it's one of the very best method to determine how two random variables are related to each other. Okay, so we will be like seeing the formula for correlation. Okay, so the formula for correlation is covariance between x and y variables divided by standard deviation of x and standard deviation of y. Okay, covariance between x comma y and square root of variance of x into square root of variance of y. Okay, so always remember the value of correlation always lies between -1 and +1. Okay, so when the value is 1, exactly 1, you can say the two random variables are perfectly positively correlated with each other. So you can call it as a perfect positive correlation when the correlation value is 1. Okay, so when the value is like around 0.8, you can say that is a high positive correlation. Okay, when the value is like around 0.2, 0.34, you can call it as a low positive correlation. When the value is 0, you can say there is a no correlation. So it's like the points are scattered around each other. Okay, so when the correlation value is -0.3, you can say there is a low negative correlation. And if it is -0.8, then it's a high negative correlation. And if it is -1, it's a perfect negative correlation. Okay, so always remember the value of correlation is always between -1 and +1. Okay, so we have been discussing how to calculate the population mean and sample mean, right? The same applies here for the population mean and population correlation, sample correlation. The population correlation is denoted by the symbol rho xy, whereas the sample correlation symbol is rxy. Okay. Okay, so we always know the correlation formula is covariance between x and y divided by standard deviation of x and multiplied by standard deviation of y. So we are just like representing with the formula of population mean, because we know it is like denoted by the expected value. Okay, and here we are like representing to the summation. Okay, so for both population correlation and sample correlation, it will be like in the range between -1 and +1. So we have a small example here. Okay, so we have a set of 5 different observations of 3 different variables: length, this is the length value, this is the width value, and this is the height value. Okay, so we have a three different variables from five different observations. Okay, so we have to calculate mean vector and variance and covariance matrix. Okay, so we always know how to calculate mean. We just have to take a summation of this. So this is the length, right? So this is the length observations. When you take a mean of these values, we get a mean of the length. This is mean of the width, and when you to calculate the mean for this observation, you get the height mean. Okay, so this is the sample. Sorry, this is the mean vector. Okay, so 4.1 is the mean of the length, 2.8 is 0.08 is the mean for the width, and 0.6 is the mean for the height. Okay, so here we have computed the variance covariance matrix. Okay, through the formula. Yes. Okay, the formula here is nothing but summation of xi minus x bar into xi minus x bar divided by n minus 1. Okay, so with this formula we have computed these values and like arranged it in the matrix format. So we call this as a variance covariance matrix. So the diagonal matrix is always the diagonal elements of this variance covariance matrix is the variance, and this is your covariance. This is your covariance, this is your variance. Okay, so variance of the length is 0.025, the variance of the width is 0.007, and the variance of the height is 0.00043. Okay, the covariance between x and y is 0.0075, and the covariance between the x and z, which is like length and the height, is 0.0175. So when you see this matrix, the values across the diagonals will always be equal. You see 0.0075 here, this is the same, and these two values are same, and these two values are same, because the covariance values, it is the same. I think you're able to understand how we have computed this. You can try it. Okay, so we just computed the mean vector and we computed the variance and covariance matrix using the formula. Okay, so now we can look into a small correlation examples. Okay, so I told that there will be like computing correlation through three different methods. First one is a Karl Pearson correlation coefficient method. So with this method, now we are trying to find the correlation between the two variables x and y, which are like follows a bivariate normal distribution. Okay, so here we have the height of the father and height of his son. Okay, so we are just trying to compute the correlation through Karl Pearson's method. So here we have the x values, which is the height of the father, y values, which is height of the son. Okay, and then we are calculating the square for both of the random variables x and y. So we have x squared, y squared, and we have product of these two random variables x, y. And then we are computing all this and finding a summation of all the five values here. We have the summation of x, summation of y, summation of x squared, y squared, xi, x into y. Okay, so now we are applying to this formula, which is through Karl Pearson's method. So we have n, we have like 8 observations, so 8 into summation of x into y, so which is this value 37,560, minus summation of x into summation of y, so which is 544 minus, sorry, into 552 divided by n into, we know n is 8, into summation of x squared, which is 37,028, minus x whole square, summation of x whole square, which is 544 the whole square. So we just kind of computing, substituting for the y values as well here, and then we got the value of 0.6. So when we know that when you say 0.6, it's kind of positively correlated. So we can say the father's height and son's height are kind of positively correlated to each other. So you can say if your father is tall, you might be tall. If father is short, you might be short. Okay, but if you have a value of 1, you can always say if your father is tall, you will be tall. But here it is 0.6. So you can say if your father is tall, you might be tall. Okay. So now we are going to compute correlation through Spearman's rank correlation coefficient method. So usually this method is used when you have the data represented in the ranks. Okay, so for example, people use this when two different types of judges are like available to evaluate a game or a contest or a competition. Okay, so we just want to know whether both the referees or the judges are like assessing the competition in the similar manner. Okay, so here we have a beauty competition happened, and then we have a rank which is given to each of the contestants. Okay, referee A for the first contestant, referee A gave a first rank, whereas referee B gave a 6th rank. Okay, so we have ranks for 10 observations. So now we'll be using Spearman's rank correlation coefficient method. So here we have rank 1, rank 2, and then we are finding out the D, which is nothing but a subtraction between the rank 1 and 2, the difference between the two ranks, and then we have D square. Okay, so we are finding a summation of the D square, which is 60. So now we are substituting in the Spearman rank correlation coefficient formula, so which is 1 minus 6 summation of D divided by n into n squared minus 1. So we're like substituting the d squared and n value here. So n is 10 and d squared is 60. We're substituting and we get the answer 0.6. So we can say there is a kind of strong agreement between both the referees while they were evaluating the game. So but if you just get minus 0.6, you can say there is like they are not in agreement in evaluating the they're not evaluating the competition in a similar manner. Okay, so their values are different. The other referees' values are different. Okay. So next one is Yule's coefficient of association. So this is a method which measures the strength and direction of an association. Okay. So here we are like using a data of a competitive examination spread, and then we're trying to find out is there any association between people succeeding in the examination in relation to attending a coaching class for that. Okay, so we have 1,800 students attending the examination. Okay, so out of which 625 students were successful. Out of this, 300 people have have attended the coaching class, and out of this 300, 180 become successful. Okay, so we are like found out this tabular column. Okay, so we have A is 625, which is a successful people. So 1,800 minus 625 is 1,175, which is people which are not successful, which is denoted by alpha. People who are successful is denoted by A. People who are not successful is denoted by alpha. And then people who attend the coaching class is B, and who have not attended the coaching class is beta. Okay, so we kind of like substituted and then found out the difference and got this table here. Okay, so only 300 people attended the coaching class, 1500 people have not attended the coaching class. Okay. So we're trying to find out, is there any association in attending the coaching class and getting successful in this competitive examination. Okay. So the formula for Yule's coefficient is AB into alpha beta minus A beta into alpha B divided by the same notations, but you have plus here. So you're substituting the values from the table here and then computing out in found you got the value 0.561, which is kind of greater than 0. You can say there is a good association in getting success in the examination when you attend the coaching class. Okay. So in order to apply this Yule's coefficient of association, you always have to construct this contingency table. Then only you will be able to find out this correlation, or I mean the association with the given data. Okay, so far we have discussed three different methods in finding out the correlation. First one is Karl Pearson's method, which is very famous method, widely used throughout the industry as well to find out the correlation. Second one is Spearman's rank correlation method. This is widely used when you're provided the ranks. And then third one is a Yule's coefficient method. With that, you have to construct a contingency table and then you calculate the Yule's coefficient association. Okay. So now we have to find out what happens if you have a lot of missing values in your data. So I'm sure you could have started using a lot of data with different factors, and then you should have come across with a lot of missing values, right? So when collecting the data, this kind of data will not be available, or it may not be relevant to add some data in few factors. So at that time, when you're calculating a correlation or computing something else, you've been applying machine learning algorithms to figure out something, you have to deal with this missing values. So in this case, you can um, deal with that through many methods. The most common methods is people delete the missing values in observations. So it is kind of done widely, but you cannot deal with that if you have too many missing values, right? And if you have a very small data, you cannot afford to delete your missing value observation. So in that case, you can go for imputation. So imputation is nothing but you are computing your missing value by applying average methods. You can either apply mean, median, or mode. If it is a categorical variable, you can go with mode. But if it is a continuous variable, you can do that imputation through mean and median. Okay, so otherwise you can do imputation through any regression methods, or you can even do apply machine learning techniques to find out the missing values. Yes, it is possible. So it actually depends on how much needed it is, how much the missing values important for your problem. Okay, so all these methods can be done. So you will be um, facing all these things when you deal with the practical problems, when you're computing you know regression or a correlation, or when you're computing machine learning, applying machine learning algorithms in either R or Python. You have to deal with this many times. So in that case, you decide what you have to do, whether you want to remove your missing values, observation, or you want to just do imputation through either mean median if it is a continuous variable, or if it is a categorical variable you can just go with mode values, or even you can apply machine learning algorithms to find out your missing values. Okay, so any questions regarding this?
No, ma'am.